Welcome. Here I am in this 3D world, and yet you see me on a 2D screen. How is that possible? To do this, we must project my image to 2 dimensions. In this video, we are not going to talk about projections on a plane yet, but start with orthogonal projections on a line. This is necessary to understand the more general formula for projections on higher dimensional surfaces. So, what do we mean by an orthogonal projection on a line? We start with a vector y and a line L. We describe this line as the span of some non-zero vector u. We need the u to make calculations explicit, but in the end the result will not depend on which u on L we choose. This means that the orthogonal projection y hat is a vector on this line, such that the vector from the endpoint of y hat to the endpoint of y, which we call z, is orthogonal to the direction of the line. The previous sentences contained 2 defining properties. Let's rewrite both of them mathematically. First of all, the vector y hat must be on this line. That means that y hat must be a multiple of the vector u. So y hat equals alpha times u for some alpha. Secondly, the vector z from the endpoint of y hat to the endpoint of y is orthogonal to the direction of the line. As u is a vector in the direction of this line, we need the dot product of z and u to be 0. If we can find the value of alpha, we know what the projection vector is. Now, z equals y minus y hat, and in this relation we can replace y hat by the expression alpha u we found. Plugging the resulting relation for z into the equation for the dot product, we get an equation which we can solve for alpha. Indeed, expanding the brackets and rearranging gives alpha equals y dot u over u dot u. Thus, we find that the orthogonal projection of y on u is given by the vector y dot u over u dot u times u. To read this formula, you should realize that dot products give numbers. So it's just the quotient of 2 numbers times a vector. At first sight, this formula is a bit hard to understand, so let us do an example. Consider the vectors u is 1, 1 and y is 3, 1. Then the projection of y onto the line through u equals the dot product of y and u, which is 3 plus 1 equals 4, divided by the dot product of u with itself, equals 1 plus 1 equals 2, times u. So 2 times u, which is the vector 2, 2. Thus the quotient in front of u is indeed the ratio of 2 numbers. And z equals y minus y hat equals 1 minus 1 is perpendicular to u, which you can check by calculating the dot product of u with 1 minus 1 and observing it becomes 0. You can now see why the value of the projection indeed does not depend on which vector u on the line L you choose. If you multiply u by a constant, then the resulting y hat remains the same. Notice that the line through u defines a one-dimensional subspace. In general, for any subspace W, it is possible to define the orthogonal projection of a vector y on W. In class, you will learn how. See you there.